Hello, everybody. Welcome to the Open Research Institute FPGA Meetup. This is the 16th of July of 2024, and we're here to talk about what we've done over the past little bit, usually a week, what we have planned over the next week, and if we have any roadblocks, anything that's preventing us from doing what we want to do, or if we need any resources that ORI can provide. So that's the goal of the meeting. And we'll go ahead and start with Ken, who's on the phone with us, and you have some updates on your efforts with the no OS approach to our platform. So if you could just summarize real briefly, like what no OS means to you, what you understand it to be, and what you've been able to accomplish, and then what you need over the next week in terms of resources or help with roadblocks. So the floor is yours.
Yeah, no OS is basically C programming, C program running on the ARM inside the ZC 706, and as opposed to the Linux build, which is running an OS, and then you incorporate features using Linux hooks. So this is the only format that TED seems to output is these .c and .h files that you incorporate into the build, and they give you a recipe to follow to do a make to incorporate those into kind of a reference design. So I did that. Finally got it to clearly try. It's clear that it's trying to pull in those files, but right now I'm still getting an error during some of the initialization stages, and not sure what that is. One of the posts that I saw Googling around was somebody was saying, well, certain parts don't run at the speeds that the TES software assumes. That might be like the lane rates on the Certus drivers. So go see if that might be related, and go back and look at the lane configuration, see if that should work on all devices or maybe just certain devices. TES is supposed to screen for invalid combinations and invalid parameters, but something about what it spits out, the actual, when you compile that on target, doesn't like that. There's a chance that whatever this is may also be related to the fact that I was getting the error trying the other path through Linux, and where you basically take the output of the wizard profile directly and you concatenate that into a Unix dev write-only file. Let's see, alternate path on that route. And, very cryptic message, and wasn't able to make much progress there, and not a lot of people have posted on that. Seems like there's more folks are doing the no OS flow, but that's the latest, I guess.
Okay, yeah, thank you so much. And TES stands for Transceiver Evaluation Software. This is a utility from Analog Devices that lets you plug and chug your desired clock rates and filter functions, filter requests, and will produce filter coefficients for you. The output of TES are these a couple of C files. So it's config.c, config.h. It's headless.c, headless.h, a binary file for the ARM, those sorts of things, and the profile. So you can go back to the profile generator and you have a human readable profile. And all of this is supposed to help program the 9009 that we're using for this particular project. So when we talk about no OS, that's a bare metal design versus the Petalinux approach that we've been trying to use. So this is a parallel effort to try to see if we can get past some of the roadblocks that we've encountered with the Petalinux approach. So Petalinux is from Xilinx, and we're happy with the way that it builds. We think we understand how it builds. The trouble we've had is as when we go to kind of deploy a Petalinux image for our development station, that the profile to program the RFIC from the analog devices RFIC can't quite get it to do it. So we've had lots of trouble here and not a lot of help. Um, the bare metal approach gives us more control over the hardware. You give up having like a embedded operating system, but the no OS approach still creates like a first stage bootloader and a couple of other artifacts. So anyway, we're going to try this and see if we can get to the point where we are writing an application, writing code. We've already been able to deploy an ELF file to the station in the lab. So Ken's work just over the past 2 weeks has rapidly caught up and possibly surpassed what we've been doing with Petalinux for over a year. So that's kind of the good news. The bad news is that we still don't have it like working over the air. We're not ordering it around over the air, but we're a whole lot closer. And, you know, we'll keep working over the next week to make this happen and also document it. What we try to do generally is to write the documentation that we would really wish we had had when we so that's kind of our guiding principle is like, what kind of documentation would we have liked if we were starting over? What would we like to see from these companies or from different communities? And that's how we create the documentation and our documents repository on GitHub. And so that brings us to the next subject is that we're in the process of moving our minimum shift keying version FPGA target version of Opulent Voice. This is our uplink protocol for the space transceiver for our satellite project. So our custom digital uplink is called Opulent Voice. It's high quality voice. That is what sets it apart from all the other options out there. It does not sound harsh or limited. It sounds great. So it's using the Opus voice codec, uh, and we picked, um, you know, so a higher data rate, 16,000 bits per second, and that's substantially better than 3,200 bits per second, which is what you get from all of the other amateur digital voice offerings. But that's not all. This high quality voice sounds fantastic, but you also get the data. So the data is actually in there in this channel. It's handled by this protocol along with the voice. So the voice gets priority because as humans, we really don't tolerate interruptions and fracturing of our voice channel. So when you have voice, it gets the priority and you hear it. And when there's any gaps or time, then you get either uh, keyboard chat, so that's a channel, telemetry or authentication and authorization that'll come through quickly and efficiently. That is very low data rate channel. So anything with authentication and authorization will be delivered. Um, and then larger data files, images, or files that you're wanting to send out over this communication system get the lowest priority. So whenever possible, the channel will be full, but voice gets the priority. So this means that you don't have to switch to a separate mode to send data. You don't have a separate packet mode or anything like that. And we view this as a big innovation over the other offerings in this space, both commercial and amateur, where you have to deliberately pick a packet mode, which may or may not work. So we do this with a state diagram, state machine, and that work is ongoing and it's looking pretty good. So we're going to implement this in a FPGA. The work for Opulent Voice with the minimum shift keying modulation is proceeding really well, and by the end of this week, then we should have all of the repositories with all of the HDL code public and published on Open Research Institute's GitHub. And so we've been thinking about how to do this because the minimum shift keying implementation of Opulent Voice is actually a set of modules. It's written in VHDL. And some of these modules are specific to Opulent Voice or specific to minimum shift keying. For example, the modulator and demodulator in HDL. But some of the other ones are very reusable. And then honestly, the MSK, modulator and demodulator is reusable as well outside of Opulent Voice. This is a very popular modulation for space. It's really cool. We're now fans of it, but it's no joke. It is complicated and kind of it can be kind of difficult to wrap your mind around it. So having a really solid open source version of a minimum shift keying modulator and demodulator is an advantage. This is our mission. This is what we're supposed to do, and putting this work out there as a standalone repository, that's a good idea. So the idea of having a library of components, a library of modules for, you know, for people to use. And also, by the way, all these modules, when you put them together in a particular way, they make Opulent Voice. That's what we're kind of after with this move from the local Git repository that we've all been working with in remote labs. We want to take this repository and not just make it a Opulent Voice repository, but expand it out into a library of modules that are useful as reusable components. And so a lot of discussion over the last week has been on exactly how to do that. And we do have an excellent approach. Uh, Matthew Wishick has done a lot of work here and has identified a script that will take his, he's the primary author for the Opulent Voice, that will take this repository and split it out into the different modules. And then we'll upload those modules as separate repositories. If you want the recipe for Opulent Voice, then there's a way to do that. So a script that will pull in all of these different components, these different repositories as submodules. So we're going to be heavily relying on submodules to kind of create a recipe from a library of open source parts. So reusability and modular approach, we hear a lot of this in engineering, that we should do this, that this should be something that we do. And we're going to take that to heart here and we're going to deliver it. So that's what we're going to try to do. Um, I'm always kind of looking for other projects that actually achieve this sort of uh, delivery, like and to try to incorporate their work and to honor their work and to direct people to their work as well. So anything that's compatible with this approach, then we'll definitely highlight, collaborate with, support, reuse. Um, we already highly recommend the FPGA utilities that Sawato does. He's the author of our DVB-S2 encoder block or project, and he already has done this. So we already have good connections and good collaboration with other people out there in open source hardware that do this. And so I'd just like to iterate that it's not just us saying, oh, hey, we're going to have a modular approach. No, we want to go out and find other people that are also doing this and make sure that we highlight and incorporate their work. So together, all of us can enjoy, um, you know, the benefits of really good open source hardware work. So this will happen over the next week. And we may try it out and find out that we need to modify the approach or edit the way that we do it. We're pretty confident that it's going to be a submodule approach of some type. So just be aware that the next couple of weeks it's going to be a little turn and burn. Uh, Try it out, see if it works. Try to find if there's, we just want this to be an easy process. We also look to analog devices and the way that they do their HDL reference design as a very important kind of touchstone, or that's a way that they've done it. We think that their method is too abstracted, that it's too kind of high centered on the on an abstracted approach to the modular kind of design. However, it's unquestioningly successful. So what we'll do is look at the way that they've done it, tie things together with Teckle, just go to a different directory to build for a different hardware. Those sorts of things are elegant and cool. And the only complaint that we have is that perhaps the analog devices, HDL reference design, their open source approach to here's a reference design to use our chips, maybe a little too abstract and also not documented well enough for just anybody to walk up that's motivated and prepared to use. So the lack of documentation we found to be difficult, and we don't want to do that. So we want to document, err on the side of over documentation to make this maybe invent a process for pulling in different Lego blocks and putting them together to make something. And we're starting with Opulent Voice. Almost all of this will also apply to Neptune, and also Hyperia, the big, the whole design for our space effort. Okay, so I know that was a lot, and uh, I'd like to go ahead and turn it over to Paul to talk about some interesting hardware things that have happened in remote labs.
Okay, got a few things to talk about. This is the probably the end of this being covered in the meeting here, but here's our warranty replacement SSD. It actually came in. They gave me no static at all. Brand new, same SSD as we had before, only this time it has no wear on it at all, and hopefully it'll last out the rest of the warranty period. We don't have any place to plug it in addition to the one we bought for replacement, so it'll be a spare in inventory for now. Another interesting thing that's gone on in remote lab lately is we were working with the no OS build, and as configured, it seems to only do serial port support for. Um, uh, Boy, it must be. I'm having a bad day. um, what's the name of that protocol, Michelle?
Oh, do you mean like libiio?
IIO. That's it.
Yeah, yeah, it
Okay, so
does.
it only does
No, no,
live.
no, no. It's good to introduce this because it's what we're relying very, very heavily on with all of our work is a library called Industrial Input and Output that is like that provides the hardcore infrastructure plumbing for all sorts of devices and all sorts of things, but definitely SDRs. So yeah, the protocol we're trying to get working with respect to the both PET Linux and no OS and applications and remote operation of our communications products is IIO. So live IIO.
Yeah, thank you. I had a blank on that. Uh, so for most of what we've been doing with IIO in the past is either local to the machine you're working on or over the network using TCP/IP, more specifically in Ethernet usually, and that has worked really well. However, the no OS version doesn't have the network stack in it apparently, and it's designed to work over a serial port. And we have serial port connectivity to the VMs, but so far it didn't work. So we spent some time trying to figure out why. So far, unsuccessfully, but it involved trying to put something else in that serial port, which is a weak point for the remote lab. We're not able to do that kind of switching automatically. We had to actually physically walk into the remote lab and swap cables around to run these tests. Um, so it may be, even though the no OS uh, seems to give us less friction for initial development, we may need to go back to the OS based version just in order to get remote capabilities. Another thing I want to talk about briefly is the remote control capability of the spectrum analyzer. We've had a capability of doing remote screenshots since virtually day one, and in the last little while, months, I've implemented a streaming video capability so you can look at the spectrum analyzer screen in real time remotely, which is much more useful than screenshots because spectrum analyzers are a moving picture. Um, but we didn't have any really good way to control it. The only way to control the functions of the spectrum analyzer would have been to write a little script in the remote control language called PyVisa. But now there's a breakthrough. This breakthrough actually came a while back from the manufacturer of the spectrum analyzer, Regal, but we didn't notice until just recently. And now with a firmware update to the spectrum analyzer, it's able to do remote control over the web. They call it web control, and you just connect to the spectrum analyzer with a web browser, and you can control it. If I can share my screen here, I will give you a brief demo, but I can't do that at the moment. Can I be allowed to share the screen here, Michelle?
Oh, yeah. Yeah, I think I can do that. Here, let me click the multiple participants. Sorry about that. Usually I do that at the beginning and I forgot. So go ahead.
Okay, good. Um, so you should be seeing my web browser now. Yes, with a Wriggle remote web control showing.
Yes.
Okay, this is what you see. You first type in the address. You have to be connected. Usually, the easiest way to do it is with a WireGuard uh, connection. Once you have that, just the URL is shown up here in the window, and you get this introductory screen. And all you have to do is go over to the left column and click on Web Control, and boom, there's the front panel of the oscilloscope or the spectrum analyzer. And you can bring up most of the front panel buttons by clicking on this thing. Here's the main front panel buttons. If you wanted to change the span, you click on span, and you get the same kind of little interactive thing, which is going to pop up here in a second, I'm sure, um, that you'd get live. Where is it? Okay, this is the first time this has misbehaved on me, naturally for a demo.
Oh, yeah, of course. But it looks great.
I'll try again. I'm clicking on span.
So, I mean, just to make clear, this is like over an easy interface to get to. It's not like before where you had to run a Python script in order to capture a screenshot and then you had to go get the screenshot. Like, this is much better.
Right. This is, and you get control. You can, so here's the span right now. Say we don't like a 10 megahertz span. Maybe we want a 10 kilohertz span. So I click 10 kilohertz, and then my span is 10 kilohertz. So I have actual live control of the spectrum analyzer. And if I like what I see, I need to make it for documentation. I can come over here to the left-hand column again and click print screen, and then print screen again. And instantly it captures the current screen, which you can then grab, just copy it off with your web browser, copy the image. Much quicker and easier than before. And there's some other things you can do here, but that's the basics. Being able to control the spectrum analyzer remotely makes life much easier if you're remote. It still can't hook up cables, but it can at least control the settings of the spectrum analyzer.
Yeah, that's a really good point. I mean, because we've done an awful lot here over the past years. This has now been up for multiple years. And we've been able to accomplish a whole lot with remote labs and bring, expensive and, kind of industry standard tools to people, directly to people. Um, but it's not completely the automation level, not complete because we still have to move cables around. And I think that's always going to be the case, because we're currently in discussions about Remote Lab South to set up our Remote Lab South with folks. And so one of the cautions is that yes, you still have to have somebody local, that there isn't really yet a pure remote lab experience where everything is entirely automated. We've gotten, I think, a lot further than almost anyone else has with respect to automating, a lab for SDRs, for FPGA, for you know RF centric, uh, equipment. But you still need people to go out there and either turn the button for on and off again. You still need to turn it on and off again. And for example, like the no OS experiments, I did have to go over and actually turn off the station and turn it back on again because it had gotten completely wedged. Or setting up an SD card. So if you want to boot off an SD card, which for some of these situations, for some of these experiments, you need to boot off an SD card. And okay, that means actually physically changing dip switches on top of the FPGA card. So you have to say, okay, this is where I boot from is actually physically changed with dip switches, or are you going to boot over JTAG? So for us, even though there's other choices, we generally tend to use either an SD card boot for the ZC706 and the ADRV 9009, so that FPGA and radio chip combination, we tend to either boot it off the SD card or we boot it over JTAG. Those are two different physical switch settings. So, yes, I mean, we could have a robot that would do it, or we could probably figure out how. But in the end, having somebody, a human resource there that takes care of your lab or takes care of your installation, you really still have to have the hand of the farmer, you know, from that old essay about farming. You still have to
Yeah, I
have
don't know if
somebody
there's something
present.
we can do for the in order to tweak the parameters that go into the output files. Um, you need to have that Linaro profile. Uh, they have like a default load image for tweaking the test software. So and that requires like manually swapping flash, I think.
Right, that's a good point. I think that a lot of companies, like the companies that we're purchasing this equipment from, that we are using their products, we're using their software. The assumption is, of course, that somebody is sitting there at a desk with their equipment right in front of them. And so, we do have to honor the limitations in the engineering of the products. So we've achieved a huge amount here, and it's done a lot of good. But the fact is that having somebody on site that can, you know, do the things that need to be required in order to in person, I don't think that we're ever going to get totally away from that. Um, and I think that we've really tried very hard to kind of achieve as much automation as possible. And at this point, I think we've gotten to the point of saying, okay, yes, a whole lot can be automated, and we put a lot of effort into it to make it easy for people to log in and to use the equipment. We're never going to totally get away from having a human resource there. And ever so often it'll crop up. Like a weird error might just be because um, the design of the software, firmware, or hardware assumes that somebody is there to either reboot it, restart it, push a button, or notice a LED is no longer blinking. So at some
Yeah.
point, I think we probably need to write that down. Like that's a good, solid article about automation. We started out Remote Labs by doing a literature review of everything in IEEE Explore about remote labs. And the vast majority were canned programs for students to do their assignments in college. And we're like, well, we want people to be able to experiment and use the equipment kind of in a more a broader, more free fashion, more flexible fashion than that. And the other side of the equation was basically just you would have a remote desktop, you'd log into a computer that was running a set of sort of hardware. Net was pretty good, but not quite what we wanted. Um, so I think that we've found a pretty solid method and proven that it works. And I think we understand like the advantages and the disadvantages and the limitations at this point. So, you know, it'd be really good if we could write a paper about the way that remote labs has worked, what's worked and what hasn't, and what we think the kind of the requirements are for a successful operation.
Yeah, as we intend to be a development lab, we can't anticipate what all the requirements are. So hooking up remote switching for everything you could possibly do would be impossible. Um, but we can always change the trade-off if we get into a situation where there are two configurations you routinely need, or some button you routinely need to push, then work a little bit of extra work can be done to automate or remote control additional things. So it's not a static thing. It's dynamic, and we're able uh, to flex with the requirements to some extent.
Yeah, this reminds me of what I saw firsthand with the Curacao uh, contest station. So there's a big, or was a big superstation in Curacao that you can rent as a amateur radio contester, and this has a really remarkable physical plant. You know, it's a dedicated building, a house, and lots of towers and antennas and lots of equipment and multiple stations within the house. And what they'd done is they'd put a whole lot of effort into the matrix of how you select an antenna per station. So there was a an amazing, you know, um, sort of a switch matrix, and you could go up and you could look at it, and after a little bit of staring at it, you could figure out like how to route each antenna to each station. So that you could say, okay, this is going to be our 20-meter station, this is going to be our 10-meter station, this is going to be 40 or whatever. And you could like figure it out, and then you could assign antennas per station. But the interesting thing was that some of the amplifiers required actual physical control. So this switch matrix, you could have automated this. You could it was actually remotely accessible, but some of the amplifiers were not. And that actually became the reason why it became kind of clear, because one of the amplifiers blew out when we were there running the station. And then, so you have to call, hey, so this is what happened. They're like, oh, okay, yeah, yeah, yeah. That's something we figured would happen, and you're just gonna have to turn it off, unplug it, plug this into this place to the. So there's there's a batch of things that you can easily automate with effort, and there's things that you can't. And I think we're getting a better and better understanding of that as we go on. And might be good to write it all down. Uh, if we if we had like here's the configuration of the lab, I think we've done a pretty good job with a couple of presentations of like showing how we do things. Um, so I don't know if we can like really like if we're at the point where we can say, okay, here's the recipe for how to do this sort of remote work. Um, I don't know. That's something that we might want to take a stab at doing, to say, okay, because I think we are going to have to come to a decision pretty quickly about duplicating all of this, or duplicating the backbone, the basic um, approach for a second lab.
Yeah, I would say that the golden hour of the remote lab is yet to come, because we haven't uh, actually developed RF circuits and hardware, and haven't needed in a well, we need some visibility, which we are able to get through going out to RF and looking at it with test equipment, but we're not actually testing the RF yet. When we do that, and have shown that you can do development that way, then we'll have a story to tell about the
Okay.
success of the remote lab.
Okay. Yeah, I see your point, and I agree, and I'm looking forward to that. And then the storytelling after will be quite nice. Awesome. Okay, so yeah, the two big things we talked about so far have been, well, the remote lab stuff is a big deal, and the evolution and replacement, and making sure that things work. And thank you so much, Paul, for all of your work here. It's been tremendous. Um, but yeah, also Opulent Voice, the transition to this is going to be a public repository. This work is it working. Uh, uh, Really amazing design. We're teaching a lot of people a lot of things about minimum shift keying, and also how to do a modular sort of design that has lots of potential for reuse. That's kind of the goal of the set of repositories. So that's a whole story there. And also Ken's work on doing a bare metal approach for the space transceiver for Hyperia, and he's responsible for the polyphase channelizer. And so this is receiving all of this cool opulent voice stuff and uh, receiving it efficiently and figuring it out and then multiplexing it together. And then that will be the downlink will be the DVB-S2 work from Swato. Um, and actually, the DVB-S2 module still has some action items, so it's not totally done. There's still some things that need to be fixed there. Still some optimizations and some development work there. So we have lots going on, um, and plenty to do. So if you're listening to this, we could totally use you, and we will support you and help you and make it work for you. The goal of all of this work is to make engineers happy and to develop some amazing, really innovative, cutting edge things for amateur radio and open source digital radio, and to just put people in touch with other people of like mind. And so we're totally happy to do this. It's all volunteer, so anything that you can do to support or spread the word is deeply appreciated. All right, so that closes out our main agenda for the day. And I will say we'll see you on Slack. We'll see you next week with another batch of work, what we've done, what we have planned, any roadblocks or any resources needed. And then we'll go ahead and move to office hours, sort of off the record. So thank you, everybody.